Okay, everybody, we talked last clip about enthalpy and entropy, and we introduced entropy as a way to think about the randomness or the chaotic nature of matter, or the chaotic nature of nature, I should say. And then basically two ideas, right? We looked at enthalpy, and again, just a quick review of the words of this and the ways we're thinking about it, is that nature favors decreasing enthalpy, right? So we were looking for a negative delta H, and exothermic, which means that processes that take place spontaneously on their own would most likely have exothermic or lose energy. And we looked at this concept of entropy, where as long as that energy is released and it's also spreading out amongst its particles in a random way, in a more disordered way, where you'd have a positive delta S or an increase in entropy, then those materials or those systems and those reactions would then produce a spontaneous change. All right, so that's fine. However, what happens when things don't go as planned, or those two ideas are not in the same state. So that's what we want to look at next. Okay, and what we can look at next is the idea of delta G. And I know we're getting a little crazy here because we're talking about a delta H, a delta S, a delta G, and we got a lot of things going on. But delta G is actually going to make things a little bit easier, because what happens when nature favors, an exothermic reaction, but then on the other hand, the entropy doesn't go up? So what happens when these things are at odds? What does nature actually do then? So again, this is going to help us make that decision. I want to bring up a little situation maybe with ice melting. Okay, if you take a piece of an ice cube or an ice cube, and you take it out and you put it on a table, that ice cube is going to melt. We all know that. Okay, so if an ice cube is placed on a table at room temperature, what determines whether or not the ice cube melts? And if we think about this, we know that number one, this is going to be endothermic, right? Because heat, in an ice cube, heat has to go into the substance for it to melt. But we talked about endothermic reactions not being spontaneous. Again, most often, it's exothermic reactions that are going to be spontaneous. But in this case, endothermic reactions are not supposed to happen according to the rule of enthalpy. But we know that the ice melts anyway. So we do know, however, that the ice, when it melts, it creates a more random state of matter. It goes from a solid to a liquid. So in that case, nature says, yes, it's spontaneous that it melts. But how can nature say no and yes at the same time? This is like asking your parents or asking two friends if you can do something, and one says yes and one says no. Like, what do you decide what to do? What is ice cube supposed to do? Are they supposed to melt or not? Because endothermic is not supposed to happen, but the entropy, the fact that it's becoming more random, says it is. All right. So again, we have to think of a way to kind of like solve this problem. All right, because ice does melt above zero, but it stays frozen below zero. So that's an interesting little tidbit on this, is that the temperature might actually play a role in this, because, hey, wait a second, if the temperature is high enough, then the ice melts. If it doesn't, then it doesn't. So maybe these two things are manipulated by a temperature, and then we can figure out what's going on. Okay, so when enthalpy and entropy compete, which means nature pushes one but not the other, the temperature is going to decide what happens. Okay, so the variables of delta S, delta H, and delta T can be combined into a special little useful equation. And again, what's nice about this is it takes three variables and makes it one variable, and this is called the Gibbs free energy. So basically, the Gibbs free energy is, what is the absolute determination? What is the absolute ending energy that can be used to do some type of useful work? Okay, is it released or is it absorbed? Okay, so that's important to know about this. Okay, so we're going to take delta G is going to be the energy, Gibbs free energy, is going to equal to the enthalpy, delta H, minus the temperature times delta S. So we get an absolute answer when there's an argument. So basically, there's only two conditions now. If delta G is negative, then the reaction is going to be spontaneous all the time, and nature is going to let this reaction take place. If delta G is positive, then this reaction is not spontaneous, and nature will not allow it to take place. If delta G is zero, then you have two reactions opposing each other, non-spontaneous and spontaneous at the same time, and delta G will be at equilibrium or zero. Okay, so important to know. Now, we're not going to get crazy and put a lot of numbers in here. We're just going to kind of look at this as a way to treat and to manage whether or not delta G is positive or negative. Okay, so there's not going to be a no, yes, or an argument anymore. It's either yes, it's going to happen, or no, it's not. Okay, so let's take this. Let's look at this a little bit more in detail. When we look at this, and we'll see. In this case, we'll take the reaction, okay, and we'll take a look at some of the relative values that can go in here. So let's just say that I look at a situation where I'm exothermic. So if I'm exothermic, nature is going to say yes all the time, right? So basically, nature likes exothermic reactions, and nature also likes the fact that things are more random. So in this case, the reaction should be spontaneous and delta G should be negative, right? As long as delta G is negative, that means it's going to happen. So if nature likes both of these and nature favors both of those conditions, then let's see how that works if we put the numbers in. Now, we could generally think if delta H is negative, so think of that being a negative number. If delta S is positive, okay, all right, and we plug those into the equation, if delta H is negative, then you're going to always have a negative plus another negative, which is also a negative, right? So delta S times the negative T here will always be a negative number. So if you take this negative number and you combine it with another negative number, you always get G being spontaneous. For example, if you take minus 10, right, and you take away 10 and you multiply it times 5, so let's just say delta S is 5, delta H is 10, okay, you would get minus 60, right? So that would be 50. Minus 50 and minus 10 would be minus 60, okay? But I'm not interested in the number. Take a look at the sign here. It doesn't really matter what this number is or what this number is. It's the signs that matter, okay? So the fact that you have a negative delta H and a positive delta S, where both of these are nature favors them, you would have to be spontaneous, okay? Now, ice melting. Ice melting is going to be more random, but it's endo. So more random, nature says yes, but endo, nature says no. Okay, so let's just put some equation, let's just put some, if we put a little bit of information into that, we're going to see that we're going to take an endothermic reaction is delta H is positive, and in a decrease in entropy is going to be an increase in entropy is positive delta S. So we have a positive endo and we have positive delta S. Now, you got to think about this here. Like this, nature's not liking that right now. Okay? But nature does like this situation where the entropy increases. So as long as this term is big enough, right? If this is big enough, then it can take over and cancel out the delta H. Again, remember, this is what's stopping us from being spontaneous. Remember, we want delta G to be negative. So in order for delta G to be negative, then this term has to be big enough to overtake the positive sign here. And that's only when the T is large. So if this T is big enough, it will cause this term to be negative, and when you add it to this, then you can absorb that positive number. Okay, so only when the temperature is large enough will this be spontaneous. Now, that's important to know for ice melting, right? If the temperature is greater enough, then the ice melts. If the temperature is low, then the ice doesn't. So 0 becomes that temperature reading that's very crucial for ice, okay? So that's the strength of this delta G, is that delta G will absorb both terms, okay? So just a way to see this as a summary. So basically, if delta S is positive, right, nature says yes, right? Nature says yes, and that's a good thing, right? We can do our little smiley face. If delta H is negative, then nature also says yes, and nature likes that too. That's also a good thing. If that's the case, they're both yeses, then the delta G is spontaneous, and this is going to happen at all temperatures. So yes, you'll be spontaneous. Nature says yes, okay, to this. Now, what if delta S is positive? Well, delta S is positive. That's an increase in entropy, and then nature says yes, we like an increase in entropy, and then nature will be happy with that taking place. However, this is going to be a no because nature does not like endothermic. It takes too much energy to do that, and nature says no. So here's our argument, our ice melting argument, right? So in that case, we really don't know what's going to happen with this However, it's going to be spontaneous at high temperature. So delta G will be negative at high temperature, okay? Because that's going to be important. So what's going to happen is endothermic reactions that are very high temperatures are the ones that are going to take place, right? Because you're taking that energy and you're spreading it out with your increase in entropy. The entropy term wins. All right, so just like that's like asking, two friends if they want to do something, and the more influential friend is the one that makes the decision. All right, now you could also look the other way. If delta S is negative, that's a decrease in entropy. You're not getting more random. Nature says, I don't want to do that. So far, we're not doing anything. So nature says, no, we're not doing that. Okay. However, we are exothermic. So nature says, yes, that's good. We're exothermic, but we're getting a increase in the energy being released. But that release of that energy must be enough to increase the entropy change. Okay. So this is going to be spontaneous at lower temperatures. Again, we don't want that. We want that sign to be negative. So I'm going to say negative delta G, okay, at low T. That's important to know. Okay, and the last combination you can think about is when nature says no. Okay, nature says no, I don't want to decrease in entropy, and endothermic nature says nope, I don't want to do that either. Okay, I don't want to gain energy and become less random. Okay, and that means delta G is going to be positive. Okay, and that's an absolute no. So this is never spontaneous. Okay, at any temperature. Okay, so really this chart is a really great way to put everything together. And again, you can see the common sense of the different scenarios. These are all the possible scenarios that can be when you have the two ideas. The key is nature favors a decrease, okay? Nature favors right here. This is what nature favors. And if that happens, then delta G will be spontaneous. Okay, so definitely go back over this if you need to and go through it. Normally, we will not be putting numbers in this. If you go to a more advanced course, you would put numbers in this. But at this point, there's a great way to see delta G. Again, it's an easy way. It's an easy way to answer that question. Absolutely, does it take place or not? Okay, and we'll see you next time.